So we can add, we can subtract, we can multiply, we can divide functions together. We can put functions within a function. We can just put integers, whole numbers, other variables. Function notation simply means, remember, you're expressing two variables working with each other. One of them is the control, and one of them is the dependent variable. So with adding two functions together or subtracting functions, it's just paying attention to like terms. Not super difficult here with your adding and subtracting. So just think about combining like terms when we're doing addition or subtraction of functions. Now, we're not solving anything yet. We're just going to rewrite the way that they look, that's all. With product, we end up distributing property. Foiling, right? If we have two binomials. So we're just thinking about distributive property for product. And then you can leave your answer in expanded form. Sure. There you go. So we're just going to leave our answer in expanded form. Although technically it's not wrong. If you get an answer and you put it in factor form, it's okay. But that's all we're doing with product. Now this one, however, oh yeah, got to be careful of the quotient. Not so much in the calculation of it, but when we talk about the domains of these sum, differences, products, and quotients. For quotients, we have to be careful when we discuss domain because what is a no-no in the denominator of a function that has variables? Yeah, can't have a zero down there, right? Can't have a zero in the denominator, so we got to be careful of that. All right. Have all that down. Sometimes the notation we use for product may be misread as a composite notation. So when we get to the composition notation, we'll show you the difference. I think that we've got it fairly straightforward on Fun Times quiz, but if there's any question as to is this supposed to be multiplication or is this representing a composite notation, then you guys can come up and ask, let me know. All right, so here we have two functions, f of x, g of x. Is that okay? You guys good? And let's see what happens when we do all four of the operations here. What do we get? And again, we're being careful with looking for the domain, and specifically on the quotients, we want to be careful with that. Now, two areas of mistakes made on operations of functions: subtraction and division. Why do you think subtraction presents a problem? I'm going to take two functions and subtract one from the other. Forget to distribute the negative. Exactly. So don't forget to distribute a negative. In fact, it's my recommendation when you're doing these, whatever your second function is, put the whole thing in parentheses so that you remember to distribute the negative. And then again, in the quotient part, we're going to be careful with our domain. We talk about the domains of those functions. All right, do we need to do A and B together, or are you guys good on those with your own selves? Are you still writing down? Should I go back? Do I need to back up now?
Yeah.
All right, let's back up. Back up a little bit. Sorry, it's a little bit too jump the gun. So we take we take f of x, we take g of x. We're going to do some stuff with them. First, we're going to add them. What do we get? Can anyone just look at it and see the answer? What's the answer? 4x squared? Yeah, look at that. 4x squared. Why? Because we're taking f of x and we're adding it to g of x, which means we're combining like terms. And I get 4x squared minus 2x plus 2x. go look at the original functions before you've done anything with them. And let's consider the domain of each of them. So 4x squared minus 2x, what's the shape? Okay, and what's the domain of every parabola in the world? All reals. All right, so we know the domain for this one is x to all reals unless we have a restricted domain. We'll talk about that when we get to inverse functions. How about this one? What's the shape of 2x?
A line.
And every line, with the exception of a vertical guy, has what kind of? All reals. Yep. So this guy also has all reals. All right, so we're just looking at those because when we put them together, I'm going to want to consider the domains of them individually and look at what I get as a combined function as well. Because maybe one of those domains is going to restrict our answer. All right, so if we look at this problem then, we have two all real domains. Look at our result. What kind of a shape do we get here for x squared? Parabola. And so the domain of this also is it's x is all reals. Not y though. The ranges would be different. The range would be greater than or equal to 0. Right. We're not talking about that. We're just talking about domains. Okay, and then we get over to B. Can you guys do that on your head? What's B's answer?
4x squared minus 4.
Yep. So now we're going to subtract G from F. So we have 4x squared minus 2x. And we're going to subtract 2x. Now because G of x is just a monomial, it's not a big deal if we put parentheses around that. However, if G of x was 2x squared minus x plus 4, I would want to put parentheses around that because when I distribute that negative, it's going to change all the signs. So it might be a good habit to get into. Put in that second polynomial in parentheses. So we see we combine like terms there, and we get 4x squared minus 4x. All right, go back to thinking domain. What's the domain of that? It's also a parabola again, right? Parabola, all real domain. So we haven't seen any issues with domain yet. Hint, hint. Coming up. All right. But then we get to this little bugger. Oh, sorry. Am I going too fast again? Slow me down. Slow me down. All right, now we have f divided by. So the function f divided by the function g. Why don't you guys, without my help, find out what that is first of all. What do you get because you take f of x divided by g of x? And then we will chat about the domain because we have to be careful here. Yeah. Got it on there? What'd you get? 2x minus 1. So we took a quadratic divided by a linear, and we ended up with a linear. Let's see how that works. So this would be the same thing as me saying 4x squared minus 2x, there's f of x, divided by g of x. So be careful here. We have to see if we can simplify that, and we can take a GCF out of the top, 2x. So we pull a 2x out, and I have a 2x minus a 1 left over. And then I have that 2x hanging out the bottom, and look at this. Oh my. 2x's, since they are both factors, can be canceled. And then we can get this. The quotient of g and f of g is equal to 2x minus 1. Now is where we need to be careful. Looking at the domain, if I ignore the original functions dividing into each other, and I simply go to the reduced or simplified answer, I will not see that I have an issue with my domain on this problem. I cannot say for 2x minus 1 that the domain is all reals. Why not? Why can't it be 0? I have asymptotes because of the g of x, right? When the function g of x is in there as a divisor, I've got a denominator with a variable, which means I can't have zeros down there. So I am considering my domain to simply state the only thing x's cannot be is 0. But it can work for anything else. Now, if we were to graph these two, and I actually graph this 4x squared minus 2x divided by 2x, put this into the TI-83. I don't have the software yet. I'm on lookout for it. I'm looking for it. Nobody seems to know where it went. If I were to graph it here, we would see that I'm going to have an asymptote here next. So here's my thing. When you guys are thinking about domains, specifically of quotients of two functions, I want you to consider the very first function you get prior to doing any GCF, factoring things, canceling stuff. Look at that problem to determine what should your domain be. All right? Can't be a 0 because in the original setup of the problem, I can't divide by 0 there. So can't have that as a part of my domain. So the quotients we've got to be careful with. Questions on that one? Now, what if that g of x was just a 4? Would we have an issue? Nope. It was just 4. Now, if it was just a constant, we're okay. Anything would work. We probably still state the domain would be all of us. But we have a variable down there, so we have to watch out for it. All right, so that's the tricky one. Multiplication-wise, right, distributive property. 4x squared minus 2x times 2x. Again, probably something we can do fairly quickly in our head. That whole thing times 2x. Do we have any problems with the domain of this one? 8x cubed minus 4x squared. What's that shape? You remember what the shape might look like? What's the end behavior? Right. Start low, end high, right? And it's got, looks like it's got a double 0 at x squared. It's going to balance. All right, but if I have a cubic, we just talked about this a little while ago, cubics, everything works in terms of domain. And the original functions, everything worked. And so in this case, we're going to say all reals for domain. Right, there are your 3 or your 4 combined functions. So combining functions, adding, subtracting, multiplying, and dividing. The composite part, which is what we're going to get to next, is the piece we need to be careful of, specific with regards to domain discussion. Be watching out for those. All right. Let me know anything we need to go over or review here on A3. Yes.
Just wondering if did you say that the factor form was okay?
The bracket form?
The factor, like factor form. Like
Oh yeah. If you wanted to write that as 4x squared times 2x minus 1, that's fine.
we don't have.
No, you don't have to. You can leave it like that. Okay, very good. Okay, here we go. Gotta be careful here. Do we remember this from algebra 2? Composite thing. So what happens in the composite world when we talk about composite functions? It's a different level, knowledge-wise, for you guys. It's a jump. It's a significant jump for some of us. That's okay. But what we're doing with composite functions is you're replacing the variable in one of the functions with another function instead of a number. That's it. Instead of plugging a 4 or negative 5 into x, you're going to now plug x plus 2 into x, or x squared minus 3x plus 4 into x. You're just plugging a function into another one. It's like the function is eating another function. That's the way I kind of describe it. So if that works for you, great. You got another way of remembering which one goes where? Let us know. So the notation for this is the one that gets confused sometimes with multiplication. Notice in the composite function notation we have this. It looks like fog, but that's really just it's like a multiplication symbol that's not filled in. So that's not an O there. And it means f of g of x. And another way you might see it written, you might think, hey, that looks like multiplication. And it's not. That is not f times g of x. When I have inside of one function another, this is a composite. So like I said earlier, it should be clear as to what I'm expecting. If it's a composite function, you'll probably see FOG type thing. Or you might see it written in this form, f of g of x, written like that. If it's a multiplication problem, gonna look probably, probably like this for multiplication. All right. Okay, so let's talk about the domain part, because this is the tricky component of this. Not so much explaining the function into another, although that is tricky. But the domain is one we've got to be careful. So it must meet, the domain of the new composite must meet these two conditions, right? The f of g of x, and here's the big one. The x must be in the domain of the original function g, and then g of x must be in the domain of the composite function f of g of x. So we'll explain what that means here in a second. Everybody doing all right so far? Doing okay? Yeah. You need to stretch right there. Let's try this. F of Q. Now, see, talk about that level of complexity. Watch this. This is amazing. It's absolutely amazing. If I were to ask you to find, let's say, the f of x function here. And if I were to just say, hey, let's find f of 2, you guys would probably know what to do with that. What would you do with that? You'd plug a 2 in for x. Exactly. You plug a 2 in for x, and you have f of 2 squared, 2 times 2. So we get 2 squared 4, 4 times 4, 16 minus 4, or 12. So f of 2 is equal to a 12. That's what you would get. And that is essentially what composition does. It does the same thing. It's just not all of our answers will be integers like that, or whole numbers. They will be other functions. So the stretch is saying, okay, let's go find f of 2 versus doing this. Let's go find f of g of x. For whatever reason, that just creates a little bit more, well, sometimes a lot more complexity in the problem. We freak out a little bit. Don't need to freak out. Okay, so how do we handle these composite guys? Think of it this way. It's the way I remember it. I have my f, and then I got a g, and then I got a 3 thing going on for a. And I notice on the very outside, I've got the f. And I look at that as the function that is eating the other one. So the function that is getting eaten, in this case, is g of 3. What I do is I find out what g of 3 is. I stick that into the f function, and I find out what f of g is. So that's what we're going to do. We're going to do it in pieces like this. So first, let's go find g of 3. Quickly, g of 3 is 6. Plugging in x with a 3, I get a 6. So then now I can say, oh, f of g of 3 is the same thing as saying f of 6. And I get less u 4 times 6 less u squared minus 2 times 6. Then we get 36, 4, 144 minus 12, 132. F of 6 is equal to 132. So that's a kind of composite answer you could have. Just a point, right? That's 0.6, 132. Let's go back, and we've talked about this already, but the domains of these individual functions, f of x, we said all reals for the domain. And same thing with the g. So here we get a composite of the two, and we just get a point. So the domain of a single point is just the x. If that had ended up as g or f of x equals 132, well, now you got a horizontal line going through 132, and that would mean everything works. But in this case, we've got a single point. So we can say the domain is x equals 6. Right? So when they're integers or whole numbers that we plug in, oftentimes we will get another integer or a whole number. But what about b? B and D are the ones that we got to be careful. And I'll let you guys do C and D on your own. Let's try B together. Talk through this one though. Does anyone have another creative way of remembering which one goes in which function? Or is it just fairly obvious and everybody knows which one goes in which? Oh yeah, there. Yeah, I understand. Julius, don't worry about it. No worries. Remember, get tired? What do we do? What do? We get tired.
Sleep.
Yeah, we sleep. What? Go around the building. Go right around the building.
Yeah,
Go around the building. Do something else. All right. Anyway. All right. Back to my question. How is there anyone else who has a creative way of remembering when I'm compositing a function within a function? How do I know which one goes where? Or are we just completely lost in that? I don't even know how to explain it. Where are we at? Are we good? So help me here. In example B, which function is the one that I'm plugging into the other one?
Well, g of x into f of x.
Okay, I'm plugging the g of x, which is what? 2x, into the what of f of x? Into the x of the f of x. Yeah, look at it. Maybe just write it this way, It's the same thing as saying f of x. But I'm replacing x with this g of x. So it's going to become 2 times something. Oh no, not 2. Is it 4? It's a 4. 4 times something squared minus 2 times something. Well, it's the g of x that goes in here and here. And we know that that's 2x. Okay, what do you think on that problem there? What's going to be a mistake people are going to make on that right now? And forget to do it for the x, or maybe you forget to square the 2. Right? That 2x is inside a parenthesis. It's getting squared, so I got to remember to get squared. 4x squared right there. So we simplify all this. We get 4 times 4x squared minus 4x's, or 16x squared minus 4x's. There's my composite. All right, domain. What do you think? domain going to be? All reals, because we ended up again with a parabola. And once again, go back and look at the originals. Their domains were also all reals, so I don't really have any restriction going on. Can anyone help me figure out when do I have to be careful with the domains of composite functions? What kind of functions are going to cause concern when I have domain, or when I'm talking about domain? Putting a function inside of another. Quotient ones, exactly. So maybe one of my functions is a rational equation, right? F of x equals 1 over x plus 2. And then g of x was equal to x minus 7 or something. In that case, I'm going to be careful of my domain. Give me another example when I have to be careful. Roots. What kind of roots specifically? Cubes are okay. So even roots I want to be careful of those. Odd roots are going to be fun. I just don't want even roots. The only thing I'm just going to be careful of is in the denominator if I have roots, I don't want to zero down there, right? Okay. Why did I leave a blank? Oh, I haven't finished filling it in. That's why. Are you talking about this one? The box. What are you talking about? This? Oh, that's just what this goes inside. That's the g of x is equal to. All right, why don't you guys do this one? Try these two for me. Partner up, do something. Somebody do that C and D, and then we'll get to some ones that we may have to be careful with. I don't know. Let's see. So try these. All right, so we're plugging the 3 in for x. We get 36 minus 6 is 30. And then plugging in for g, plugging in this 30, and we get 2 times 30, or 60. So, the question is the domain? Yes. So, all right, and then over there, and the next one, you guys said it was 8x squared, what, minus 4x? Is that right? Yeah, so we plug, this time we're plugging 4x squared minus 2x into the g function. So 2, 4x squared minus 2x. And there's my composite. What's the domain on this one? Yep. All right. Well, then what if we start introducing the roots? So we mentioned just a little while ago that the ones we have to be careful with for domains are rational equations. We have variables in the denominator, and radicals of even roots. And so those are the two that can present us with some challenges on the domain. So why don't you tag team on this one? Find a third partner. When you do A, when you do B, when you do C, and then have each other look at it and see if they did it right. All right, so for C, showing that f of h of x does not equal h of f of x. X does not equal -1. So let's go find f of h of x. That's going to be equal to, we're going to plug in the h into the f. So I'm going to take into x cubed will be a cube root of an x plus 1. And then I'll have a plus 1 stuck on the end. Cube root of cubing a cube root just gives me this. So I have f of h of x equals x plus 2. Cool. So find the other one, the other composite function, h with f of x. What does that equal? Now we're going to plug f into h. So within the cube root world, and here, we're going to plug the f of x, which is x cubed plus 1. And we still have x there. And then simplifying this underneath the radical, we got x cubed plus half of x. Now they're obviously not equal to each other. So let's go solve them. See what would the answer for x have to be if they were equal to each other. So if they were, then we would get that x plus 2 was equal to the cube root x cubed plus 2. So what we're trying to do is find out what would the value of x have to be for these two to be the same. And we're going to kind of do a converse thing. So if I want to undo this cube root, I got to cube both sides. If I cube an x plus a 2 cubed, it's like saying x plus 2, x plus 2, x plus 2, or using Pascal's triangle, I have 1 x cubed plus an x squared times a 2. Oops. I'm just using Pascal's numbers 1, 3, 3, 1, since I'm in row 3 there. And then 3x squared times 2 plus a 3x times 2 squared plus 2 cubed. X cubed plus 6x squared plus 12x plus 8 would equal x cubed plus 2. And then solving x cubes are going to cancel once I get everything on one side. 6x squared plus 12x plus 6 equals 0. Get a 6 out of there. X squared plus 2x plus a 1 equals 0. Factor it. X plus 1 squared equals 0. So that means x would equal negative 1. So that's what it would have to be for them to be equal. So therefore, if they're not equal to each other, that's only going to happen if x does not equal. That's true. We just verified the answer.
Your final answer would be like to show that it is not equal.
That they do not equal each other if x does not equal negative 1. Well, we